name is Kathy. I'm here today to talk to you a little bit about quarks and let you know something about what they are, how they behave, and that sort of thing. So quarks then, why are they important at all? Well, quarks make up 27% of all matter. So everything that's around us and everything that we are is 27% quarks. So that makes them pretty important as particles go. And they have some very strange features about them, behaviourally. So that's what we're going to talk a little bit about today. There are two distinct camps of research, if you like, or experimental study on quarks. And those two camps are QCD, which is quantum chromodynamics, and QED, which is quantum electrodynamics. So this covers all the variants of quark mixing, as it's called. So let me explain a little bit about what quark mixing means. In the colour system, the QCD bit, quarks come in three colours. This is just for convenience, you understand. It's an analogy to allow scientists to get their head around how quarks behave and what they do. So they've assigned them these colours for ease of use, if you like. Red quarks, green quarks and blue quarks can morph into each other, okay? So you can have a green quark becoming a blue quark, or a red quark becoming a green quark or a blue quark, or vice versa, or any permutations of the above, alright? All of them. And they happen all the time. Quarks are in a continuous state of flow from one thing to another. They go from red to green to blue, etc., etc. So they're always doing this. Now, what enables them to do this is their connecting partners, if you like, the little bits that stick them together, which are represented here by these colour streams flowing from one colour to another. That actually represents a particle in its own right, which can't really be called a particle because it's a force carrier, alright? And it's called gluons. Hold quarks together, they bind them, hold them tightly, by means of something called the strong force. Now there are four forces in nature. There's electromagnetism, gravity, the strong force and the weak force. So as far as quarks are concerned, they are held together by the strong force via gluons. Okay, so all this is happening, colour changing from one thing to the other. In the meantime, you've got to also remember that quarks come in three pairs. They always exist in pairs, quarks, under normal circumstances, unless you're smashing particles to bits in the LHC, in which case they can fly off all over the place and it doesn't count. But under normal circumstances of nature, you will find quarks existing generally in pairs, but in threes. So you can have two ups and a down quark, or an up and down and a strange quark. Okay, all sorts of permutations of the flavour of what quarks can be. So these are the flavours then. Up and down is the most common one, apparently. Then you've got strange and charm quarks, which managed to keep their names. And then you've got these two, beauty and truth, which were the last two to be discovered. And they were named beauty and truth when they were discovered. But then very soon after that, scientists started to call them something else. So the beauty quark became bottom, and the truth quark became top. So now, very often in scientific papers of all descriptions, wherever you see quarks written out, you'll find bottom more commonly than beauty, and top very, very much more commonly than truth. Beauty is starting to creep back into the scientific language now, which is a real blessing. I'm very glad to see that's the case. And long may it rain, because these are the original namings they were given. So this is what you get in quark flavours. You also have, of course, their anti-quarks to consider. So every one of these has their own anti-quark. You've got anti-up and anti-down and anti-strange and so on. They all have their own anti-quarks as well. Okay. So just to illustrate a little bit more about this flow of change that keeps on going on, I've got a little diagram in the middle here, which is a spiral, as you can see. It's called chirality in physics. And essentially, this represents oscillation. Oscillation is something that quarks aren't particularly famous for, but neutrinos certainly are. Neutrinos are those particles that you might have heard of that stream through us from the sun. Billions upon billions of them are streaming through every tiny centimetre of you all the time. They are the commonest particle in the universe, apparently. Although there has been recent research to suggest that neutrinos don't exist, but we won't even go in. We won't go there. No. So anyway, this is oscillation, which is what neutrinos do. For our analogy here, we're using quarks in the same way because it's the same kind of behaviour. Alright? So here you've got a red quark, and then you've got a couple of loops, and it's turning into, hey presto, it's a green quark now. And then just a little while later, it's a red quark again. That could easily be a blue quark or whatever. The colour is irrelevant. This is just an illustration. So this oscillation that happens in the neutrino field also happens in the quark field. And interestingly enough, Symmetry magazine actually said quarks are waves in the quark field, which kind of leaves a little bit of a question mark as to whether quarks are really particles at all. If not, what are they? Because 27% of our mass is made of these things, so we ought to know what they are really. Okay, so what I'd like you to do is to go off and find out as much as you can about quarks and how they behave, the oscillation features, the corresponding things with neutrinos. See what you can kick up, yeah? But before you go, there's just one other thing that you really need to know, because I'd like to go into the QED bit now, the quantum electrodynamics of quark mixing. So up and down quarks, these are the most common ones, remember? They are standard quark size, okay? Common quark size, that big. And they're measured in electron volts, which are represented like this. Little big V. Strange and charm quarks, well, they're a bit bigger. Let's say they're that big, for argument's sake. So they're plus EV in my language, alright? They got more electron volts. If you want to know the numbers, please go and find out what the numbers are, because they do correspond. There are papers everywhere to tell you all this stuff. But beauty and truth quarks, well, they are huge, absolutely humongous by comparison, for instance, to up and down quarks. So these are gargantuan. Right. They get then this. I shall assign them extra large EV. Okay. So, without any numbers or maths or equations, this is essentially how quarks work. Question is, how does that relate to us? Because obviously we're made of these things, and if they're changing and oscillating and moving about all the time, how does that affect the way we are? Is there a correlation? The other question is, what about this neutrino field that's also fluxing in through our quark field all the time? Could there be some kind of information exchange going on? We don't know at the moment, so that's worth investigating. So anyway, this is quarks in a nutshell. Next time I'll talk about photons, and if you'd like to know more about this kind of stuff and join in the discussions, please come and join the group Quantumology on Facebook. You'll also be able to follow Quantumology on Twitter if you want to, and if you go into your search engine and put in Quantumology, you'll come across the website, so feel free to have a look around there as well. Thank you very much indeed. I hope this has been fun, and I'll speak to you again soon. Bye.